Okay, good morning, everyone, and welcome to the scientific visualization course organized by CSCS. Actually, it was organized by Jean Favre, and you should have received an email with your credentials to access CSCS systems. If you didn't, please write in the Q&A to tell us that you don't have access to the systems. Also, please use the Q&A for any questions that you might have during the course. So together with Jean, we have a few colleagues that will be also attending the course, but volunteer to help in case of some issues with the CSCS systems, in case Jean will be busy with the lecture and answering other questions related to the visualization part of the course. So I think that's all from my side. I'd like to give many thanks for Jean for preparing the material. So with that, unless you have any burning question, which you can also do by raising hand. So you have this option. If you're new to Zoom, you should have the option of raise hand, and Jean will see this, and he will allow you to talk at some point. So he might not see immediately, but he can unmute you and allow you to talk if you want to have your questions through audio. Did I miss anything, Jean?
Yeah, I think we're good.
Good. Okay, thanks. Over to you.
Okay, so wait a second. So good morning, everybody. There's a little bit of confusion here. I have two screens. I have many apps running, so please bear with me if when I'm hesitant about things. So I'm going to start sharing my screen right away, and this is where. Okay, there we go. Share. So the program of today, I hope I'm pointing here to the web page on the CSCS website. So this is a completely new course from my point of view because we're doing this remotely. So we had to change the program somewhat. It's not as intense as in terms of hours, we're going to have fewer sessions, and I hope things that are not too heavy. And then concerning the content, there's a lot of new stuff, and this is what I'm very excited to present. So because and the new stuff really concerns Jupyter Lab notebooks and the use of ParaView and some other widgets, as we will see, to do visualization directly on our web page with the Jupyter Lab support. So because of this, I've changed basically a lot of my content. And because of this, the overview that we're doing here from 9 to 10 is going to be something very brief to give you a couple of ideas about applications to do 3D visualizations at CSCS. And it's going to be indeed, very quick. So if later on people wish to really get much deeper into one of the particular topics I would present, I would do a survey, and then perhaps we could propose maybe next month another webinar dedicated to the particular application. So from 9 to 10, Echo, this is the current time frame. We're going to look very quickly at ParaView, VisIt, VTK, remote desktop to do OpenGL applications, and then Jupyter notebooks. And then here I will actually spend quite a bit of time showing Matplotlib animations to make sure people have at least this level of understanding. And then from 10 to 10:30, indeed, there's a typo here, but we'll give you a little bit of a break. So we'll stop here, and then at 10:30 we'll start again talking about well, the original title was 5 formats for scientific data visualization. But there's so many 5 formats, and in fact, each of you has probably a very particular need. So I would be wasting your time if I talk about, for example, HGA5 to people doing molecular science, and if vice versa, I talk about the protein data bank data format with people doing fluid dynamics. So I've taken a very different approach, which is new. But just to give you the feeling about some important point with data formats. And then indeed, next week, my colleague Samuel and myself actually will have another webinar on Parallel IO, and this will be an opportunity to to talk more in depth, for example, about HJ5, about ADIOS, about those formats. This will be for this morning until 11 o'clock. Then at 11 o'clock, I will start really digging into the ParaView application. As you know, ParaView has been really the workhorse of 3D visualization at CSCS. We've used it for many years on some very important projects, and I will give here the introduction to the application. Specifically, we will also talk about importing NumPy arrays into ParaView, because I suppose a lot of people doing Python-based computation, be it on a Jupyter notebook or on a more standalone application, people are very interested about importing NumPy arrays, Dask arrays, I mean, all those families of Python arrays into the ParaView application. Then in the afternoon, we'll go through some particular algorithms and methods with ParaView. So the classic stuff, scalar, volume, vector field visualization, time dependent, quite a bit of Python scripting. And for that occasion, in fact, we've asked each of you to install the ParaView application on your desktop. Now, I hope you've had no problem with that. And we will use ParaView both standalone and then in connection to the PitsDaint ParaView server. And then tomorrow morning we'll do something that I like very much, which is pretty advanced. We'll do photorealistic rendering for 3D visualization. And this is the use of ray tracing, path tracing, ambient occlusion, all those advanced graphics methods which we have at our disposal, running both on the GPU or on the CPU, on the CPU multi-core partition of PitsDaint. And you'll see that we do manage to have interactive photorealistic rendering, so that makes it really very exciting. In between those different sessions, we have time for breaks, we have times for Q&A. So I ask for your patience. If there are too many questions coming, then it might be difficult for me to answer things in real time, but we'll try to do it as we go. Okay. So let me switch now presentations and share another screen, which is this particular one here, and that's the beginning of my presentation. So I'll start with this overview of applications at CSCS. As a preamble, all the code and documentation is available at this particular GitHub address. So you are encouraged to clone that repository, and it will have the PDF documents which I am presenting here online, It will have Python notebooks, Python scripts, and some examples for ray tracing, for ParaView, for Jupyter, for Matplotlib. I have tried in my slides to highlight in purple all the example files, demonstrations files, which are available on the repository. So you should be able to have those exercise and demonstrations for your own usage during the course. Now, I've also tried to make quite a few examples which do not require specific data to be read. I mean, it generates data on the fly, so it makes it very easy to deploy the exercise on each of your different operating systems, etc. So I hope this will work well. Finally, on the user portal, we have a visualization chapter, and there's also pointers here on how to run our different applications there. So the outline, I'm going to shock a few of you. I'm going to present VisIt in only 2 slides. Okay, and this is in fact the point. If people want a much longer webinar, we could most certainly organize that at CSCS in the near future. And we'll present ParaView also in 2 slides. Then I will present VNC remote desktops, talk about VTK, because VTK is mostly everywhere in advanced 3D visualization. And I'll tell you how to get to VTK on the PITS Day installations. And then we'll talk about Jupyter for the rest of the presentation. If you have help, you can raise your hand, you can ask questions. And if really this is too much, again, please send mail to help@CSCS. And in the next following days, we will get to address your concerns or your issues. So VisIt is one of the 2 very common visualization packages available at supercomputing centers. VisIt is open source, platform independent, distributed, parallel, and it enables a very wide range of visualization methods. So VisIt has been in use at CSCS for many years. I have taught VisIt specific tutorials many times, not only at CSCS, but also at different computing conferences. So again, I am available for anyone who wishes to go more in depth into the VisIt application. Oops, sorry about that. So we have version 3.12 available at VisIt. This is the latest version available. And if you install a binary precompiled on your desktop, instructions are given on our website here on how to get a copy of the host profile for PITS Date. If you install that on your home in the directory called .visit/host, I have prepared for you a script which will automatically connect to CSCS. So that particular script you find in the repository. It's called connect_dane.py, and you use it in the following way. From your desktop, you run VisIt -cli for the command line interface and -s for the option to run the script. And basically, how do we organize this? On Date, you load the module Date MC and the VisIt module. And once the particular module has been loaded, the environment variable EB root visit is defined. That variable holds the directory where VisIt is installed. And this is actually very important because this is the variable we need for the connect date Python. So it needs to be explicitly copied into the connect date Python script. If we go further into the options, we have here for an example where we're using 8 tasks, 1 node, 5 minutes. This is to run very quickly. And then here you can put additional options. For example, your reservation or your account name, the partition you wish to use. For example, here the debug partition. And then you open basically the computer engine at the address date101.cscs.ch with the following arguments. So all of this is done by the Python program I have made available. So people interested about using VisIt should try this. If there's any issue, please let me know. But I've been using this for many years. This is part of our automated testing routine, so it should work pretty smoothly. If I go now to ParaView, ParaView holds the same characteristics. It's open source, multi-platform. Just like VisIt, ParaView also allows batch processing. Okay, this I hadn't mentioned that earlier. And just like VisIt, the batch processing of ParaView is based on Python. So this is why we put a lot of emphasis on the Python programming language. Now, of course, ParaView, just like VisIt, was developed to analyze extremely large data sets. So what do we mean by extremely large data sets? We mean data sets that do not fit on a single compute node. Now, on Pitts date, compute nodes have 64 gigabytes of memory on the normal partition, and we also have some a fat memory partition, as you should know, with some nodes holding 128 gigabytes of memory. So it's already pretty big, and it would be actually one of the first advantages of using the remote facilities on Pitts date. Pitts date will give you compute nodes with a pretty good memory capacity, and also GPUs. Perhaps on your own desktop, you don't have a very good GPU available. So this is an incentive for running the applications remotely at CSCS. ParaView version 5.8.1 is installed at CSCS. This is also the current release. Now, just like VisIt, the client-server connections of ParaView is done in a reverse connect fashion. What does that mean, reverse connect? It means that the client on your desktop initiates a connection to CSCS. It creates an SSH tunnel, and then it submits a batch job to the queue. Once the batch job runs, some compute nodes are available, and the first node of the allocation actually connects back to the client using the SSH tunnel. So this might seem pretty complicated already, but we have an automated way of doing all of this, either using the GUI client or using a Python script. Now, the Python script I have made available on the repo is actually here. This is something I have tested only for Linux users at the moment because I just didn't have time to do more. This is something very new, so it's experimental, but I seem to have it working pretty well. I also look forward to your feedback on that, and then I also look forward to your feedback, Windows users or Mac users. There might be some other details to organize to make this fully automatic. We'll go in a lot more details about ParaView in the rest of the discussion today and tomorrow. Now, VNC remote desktop support, that's something else that we have at CSCS. And this will basically allow you to run any OpenGL application. Of course, we have specialized and dedicated support in our staff, namely myself, to help you with VisIt and ParaView. But should you have the desire to use another OpenGL application, which you can install in your own home, in that case, the VNC remote desktop is the perfect solution to have an allocation with a compute node and a GPU and an X server available. So this is documented also in our website at CSCS here, following the particular link. And basically the key ingredient to all of this is doing an allocation of a GPU. This is something that most of you will be very familiar with. But in addition to the GPU, we have an option to start an X server. So running an X server means that we can run a normal standalone VNC OpenGL application. So the particular job, we have an example batch job available on that web page. And basically what it does, once the job is submitted, the output of the job is the following two lines. The SSH command that you should do to create a tunnel. So in this particular case here, this need 03511 is the ID of the compute node allocated. So we create an SSH tunnel to that particular node. Of course, username would be your own username. And then using, for example, the VNC viewer locally on your desktop, you are able to connect to the remote VNC desktop. So I have one of them. I have one VNC desktop already running, which I will demonstrate to you. Windows users do something very similar. They open an SSH tunnel using the PuTTY profile. So using the same characteristics here, the same numbers, we would create with PuTTY the following profile. I have it on my next slide. So this is what you would do in your tunnel. In the tunnels option of the SSH connection, you add this particular line. This is a local tunnel, okay, and that enables you to get to the VNC remote desktop. So I have one of them running, which I'm going to look for. Let's see. I need to share this particular. There we go. I have lost myself here. Just a second. Okay, people should be seeing this particular desktop I have here. So basically, I have here the VMD application, which is used for molecular science, and I am running here a simple model showing you how the 3D graphics is working inside the remote desktop. So let me quit the application because I want to point out the look of it. So this is the remote desktop. As you can see, you have your full home mounted on the node. You also have as you can see here, the GPU available. So this is pitch date. So we have the driver 440 from NVIDIA running on the GPU. Now, we are inside the VNC desktop, so all applications should be run with the VGL run prefix, as you would know. So I run VGL run. The name of my executable, this is VMD in that particular case. And as you can see from my console display here, indeed, the GPU, here we have the GPU and the multi-threaded characteristic of our compute node detected correctly, 24 CPU threads detected, and a CUDA device, which is here the Tesla 100 node. All right, so that's basically it for the demonstration of the VNC desktop. As you can see, I have really the full applications available to do graphics. So VMD is a pre-installed package. However, you are free to run any other package requiring OpenGL and NX server. All right. I'll come back here and share again my my other presentation. Let's see. This should be just a second. Okay. This is what I'm sharing now. So I'm back on the VNC remote desktop page. Very good. Now, VTK, since you are watching this particular webinar, I imagine that you've heard about VTK, right? VTK is, from my point of view, VTK is basically everywhere. There's not a single day that I am at the office without me using some parts of VTK. Now there's a nice address here, VTK in action, on seeing the different uses of VTK. Now VTK is both how would I say, a library. It's also a data format. VTK is at the base of it a C++ library, which is available in VisIt, in ParaView, and in Jupyter Notebooks, as we will see in the rest of our presentation today. So in particular, at this particular address, I will demonstrate the use of the ITK widgets today. And the ITK widgets is really a nice Jupyter Lab notebook widget, which enables us to import any VTK-like object. We'll see more in our demonstration. Now, VTK can be used as a standalone package using the VTK Python executable. Typically, we use VTK Python. However, at CSCS, since VTK is included in ParaView, it's enough to do a module load ParaView. And if you do that, you will see that this particular address here is added to your Python path. So you can then use the standard Python interpreter. And yeah, in fact, at this particular Python path address, we have the MPI4Py package, the ParaView package, the VTK module, and indeed the VTK.py module. So you can load the ParaView module and then access VTK in that particular fashion. Here, you use your standard Python 3 interpreter and you import VTK in the normal fashion. And then this is an example here on the right page, on the right side of my page, an example doing using the VTK syntax in Python to do some analysis. So at the moment, with the ParaView we have installed at CSCS, the VTK version we have is 8.90. Should you need a version that is more advanced, we have also a specific module for VTK for version 9. All right. So now let's go on the completely new stuff, which I am very excited to propose. This is the support of visualization in on Jupyter.cscs.ch. Now, Jupyter Lab at CSCS has been presented already in the past, I guess last month when we had the user day. Tim Robinson and Raphael, my two colleagues, presented the deployment of Jupyter Lab at CSCS. So I would refer you to the video recordings of that particular session if you want further details. A Jupyter Notebook is basically an open source web application, as you would know, containing both codes, equations, visualizations, narrative text. So it makes it very, very interesting to do prototyping. And also, in terms of teaching, I have found that it's a very nice platform to actually do step-by-step visualization. So we'll see how this works. We have a dedicated page at CSCS called Interactive Jupyter Lab Support, and then we'll see how we get to it. On the Jupyter, for this particular workshop today and tomorrow, we have created a reservation. So most of you, all of you should have received the credentials to log in onto the system. And what you should do on the jupyter.cscs.ch page, you should use the visual course keyword here for the reservation. And then you are also encouraged to use the 2.02 version of the Jupyter Lab, because I have tested all my examples and demonstrations using that particular version. We'll be using the GPU. This gives us both the opportunity to test hardware accelerated rendering and also some multi-threading support, which we will use for ray tracing, for example, tomorrow. Using the GPU gives us, in any case, 24 compute threads, as we've seen already earlier. So this would be the basic page we will use for Jupyter. Now, a very first introduction to do some animation in Jupyter would be the IPywidgets. I suppose some of you are already familiar with that. The IPywidgets are basically some really nice eventful Python objects which we can hook up to callbacks in our computation script to create interactive GUIs. So it's really something very simple, very easy, and I would say very sexy to use, because it makes for some very nice demonstrations. I've included here the page that you should refer to for the basic presentation of the IPywidgets. What we will use in the different examples I have created is the interact function. The interact function is something indeed that creates the user interface controls for exploring code and data interactively. So I have here tested an example which I have gotten from the internet called Exploring Lawrence. This is in the repo that you should have cloned, and we'll have to make sure that each of you can run that example. Prerequisite to do this and the following exercise at CSCS. If you've never used Jupyter Lab, this would be something important to watch. In your home, there should be a file called jupyterhub.environment, where you can put additional instructions for the server to load. So in the case of this particular workshop, we will use the module PyExtensions, which provides Matplotlib, for example. We will use H5Py, so I've selected that particular version of the module. We will use ParaView. We will use FFmpeg. Now, later on, after the workshop, when you use your allocated budget at CSCS, it does not matter if you're using the MC partition or the GPU partition, because in both cases here, the ParaView module will load the appropriate module either for the MC partition or for the GPU partition. So this would be all that is needed to run ParaView. And then optionally, you know that you can also create a virtual environment at CSCS where you can add additional Python modules to the standard modules we provide. So if you have a virtual environment, this would be, in my case here, this is something that would be personal to your installation, but in my case, I run the activate executable from my particular installation. So somebody is asking here, my home does not have the file .jupyter.env. Okay, there, this particular file here. So of course, if you've never used Jupyter at CSCS, and if you're using the course accounts, probably that file does not exist yet. So it basically just has to be created new. Okay. So what you would need to run the examples at CSCS is indeed those different modules. So basically what you could do is copy, instead of home here, you could copy from my own directory /users. I will type the answer here for everybody. Copy /users/Jean-Fab /.jupyterhub.env. You copy that to your home. Okay, there. Let me go on with the presentation. So the first example I have created, and at this point, I'm going to get an allocation, and I'm going to open a page at CSCS on Jupyter, on the Jupyter Lab server. So it will take a few seconds here for me to start. And this example is using ParaView. So the standard ParaView Python, and the most trivial example that it's basically the hello world of ParaView. That example creates a sphere and lets us animate that screen in 3D. So what is necessary in Python to do this? In the Jupyter Lab notebook, the first line of code here is importing the ParaView module. This is very standard. We create a sphere object here in our second line of code with a resolution both in the latitude and longitude of 32 grid points. And then we show that the show command is a command that we will use in ParaView every time we want to display something on the screen. And what is new, and this is the PV display widget. This is something that was contributed by NVIDIA. And with those 3 lines of code, which again we will repeat in all our demonstrations, we will run the graphics, we will run the ParaView rendering inside our Jupyter notebook. So I'm going to demonstrate this. I have now unallocated. I'm going to switch screen for a second. I'm going to share this page, and I am here on the first example I have provided view. So this is, by the way, if you have your own Jupyter Lab installation on your desktop, this is something you can also do locally because it does not require anything specific to CSCS. But here I am running it using our allocation. So the first point indeed is to load the ParaView module. This was done here. I create my object. I create a render view, and then I pass this render view to the PV display widget. And at this point, as you can see from my screen, I have a fully interactive 3D animation. Okay, so there's nothing else we can do here. This is the Hello World probe demonstration of ParaView in a Jupyter notebook. But as you would know from Python, I can now do anything I want with my sphere object. So for example, interrogate my sphere object, its resolution is 32, and change that resolution to 8, for example. And as you can see, immediately my image here has been updated with the new resolution. So that's the first example. Let's see now how we can augment this particular demonstration with the IPywidgets. So I'm going to close this and go to, as you see from my screen here, go to the second example, Hello Sphere ParaView.1. Basically, the same thing. I'm going to import my ParaView module. There is here some standard diagnostic, which I have put in here just to demonstrate to you that we are indeed running on the Tesla P100 GPU at CSCS. I'm creating my sphere again. I get my render view. This is what we had already in the previous demonstration. I'm going to create a new view for this output to put here on the side. It's a little bit more comfortable to work with. And here's the demonstrations of the IPywidgets. I'm going to use the interact function that I talked about, and I'm going to use an integer slider to do exactly what I had done earlier to modify the resolution of my sphere. But now, instead of doing this at the command line, I'm doing this using a graphical user interface. And you're going to see that this is very nice now because we have here a slider with a resolution of 12. And as I move my slider around, I change the resolution of my sphere. And this is a fully interactive view, as you can see here. So basically, that's all there is to it here. Define the callback function, which I have called here sphere resolution. It takes a single argument, the res integer, and I'm modifying both the theta and the phi resolution. Now, the first exercise you should do if you've never used IPywidgets is to modify this particular demonstration to use two different sliders, one of them for the theta resolution, the other one for the phi resolution. So I'm going to do this interactively with you so that we can practice this. And then you'll have to do this. You'll have to try to repeat this at home later on. So I'm going to change this, make this a 2-argument function, resolution 0, resolution 1. I'm going to change that slider to be called resolution 0, and I'm going to copy this to be called resolution 1, and there we go. I have now a graphical user interface with two sliders. One of them changes the phi resolution, the other one changes the theta resolution. Okay, so I recommend you try this example, and then you report to us if something doesn't work. And let's see, there's some question here. I have to verify that. So the question is there a way to add the standard control buttons and properties directly within the PV display? And my understanding is that at this particular point in time, this is not possible. No. Indeed, the PV display widgets contributed by NVIDIA at the moment is something where there's no further development done provided by NVIDIA. And my understanding is that Kitware, the company which is developing VTK and ParaView, Kitware is or will in the next future do further development on that particular widget. So from the NVIDIA part, my understanding is that the development is currently frozen. All right, I'll switch back to another screen just to get back over here. There, so we've done our basic ParaView IPywidgets demonstrations. In summary, what have I done? Given the sphere example, given the sphere object, all objects in ParaView have a function called list properties, which gives me a list of all the parameters which can be modified with the object. So the phi resolution, for example, and the theta resolution are two of the parameters of that sphere object which I can modify. So what I have done in my particular demonstration here was to attach those two integer arguments to an integer slider. We've seen that in the code already. Basically, for each slider, for each GUI control events that you want to control, you have to define a callback, which refers to the object which you want to control, here the sphere object, and then you pass the arguments as I have done here, in the callback. So there was the exercise. I've done it for you interactively, and you are now encouraged to try the same. And to in the exercise, in the demonstrations I've given you, I've actually demonstrated how to use two sliders to change the theta resolution and the phi resolution. What you could do as another exercise is, for example, here, the radius parameter is a floating point number, which you can also modify to change, indeed, the radius of the sphere. So you could try this as an alternate exercise. Now, let's go to Matplotlib animation. Matplotlib is something when I started working with Matplotlib, I thought this was a pretty cool widget. So I also encourage you to use it, and I wanted to demonstrate that also to you. What we've done, which was new on PitchDaint, we have recently added an FFmpeg module. And this is what I want to demonstrate to you using the Matplotlib animation notebook, which I have put in the repository. So I will switch back once more to my live Jupyter notebook. I will stop here the ParaView stuff, and I will go to the directory, the folder called Jupyter Lab, and here find the Matplotlib animation notebook. This is again an example which you can run standalone on your own desktop if you have already Matplotlib, etc. available and installed. So I'm importing Matplotlib in the standard fashion, importing pyplot as PLT, and here importing from Matplot the animation module. So we're doing this. We're going to do basically a standard figure with something very simple. As you can see here, we have defined in this animate function an x-axis going from 0 to 2, and in a function y, which is numpy sine of that particular function there. And to animate this using a Matplotlib animation function, we define it in the following manner. We provide the figure object, we provide the callback. To initialize the function and the figure to the proper setting, we provide an init callback here, which sometimes can be optional. It will depend on how you set up your code. And then we say, I want 100 frames with an interval of 20. And this blit option in the func animation call set to true is something that will greatly accelerate your animation, in the sense that it will not redraw the part of the figure that don't change from one time step to the next. Now, by default, as you can see here, I've executed the animation cell, but there's nothing on my screen. It's because there's no, using the inline display, there's no display directly inside the widget. We can verify that by looking at the representation HTML, which is in fact set to true to none at the current time. And the key to doing an animation on the screen is actually to change this to JavaScript HTML. This is the particular thing we will do here to show our animation online. So it's going to take a few seconds here to set up my animation. And I now have my figure, and then a nice GUI panel to animate my particular function. So of course here it is pretty boring function, but we will use this to do some more advanced visualization. So of course you can go back, you can go forward, etc. Do all those fancy things. Now the FFmpeg module, which we have recently added at CSCS, comes to play at this particular point in time, where we can save exactly the same animation. Here the animation object is called anim, we will save it locally, locally in your home or anywhere else on the CSCS file system. You can save it using the particular writer video, which you define as an FFmpeg writer with a frames per second set to 60 and a codec. The default codec here is MPEG-4. So if you do this in the Jupyter Lab notebook, which I have provided, you will end up here. I have it done. You will end up with a movie file written into your home. I'll switch again screens and share my presentation over here to go back over here. So I've prepared a case study with the Hurricane Isabel data. That case study will provide us some motivation for exercise to try again the IPywidgets, to try the ITK widgets, which is something new which I want to show, and then we'll do some exercise as well. So there, Hurricane Isabel.
Jean,
Yes?
just before you continue this, I think there is a little bit of confusion about how people should launch the Jupyter notebooks.
Okay.
Perhaps you could just show the jupyter.cscs.ch again.
I will do that. Thanks, Tim.
Yeah, thank you.
So first, back to my screen here on page 16. What you should do, and I will demonstrate that, you should use those two parameters, visual underscore course for the name of the reservation, and then you should use the Jupyter Lab version 2.02. So let me demonstrate that immediately. I will switch screen, stop, and then share over here. This is my web browser. So I'm going to type jupyter.csch. Yeah, I guess I had a server already running. So if I go to my hub, I can close it. I'll do another one here.
You're doing the TDS, right?
Yes, that's right. I just realized that. Sorry, guys. So I'll just come over here. There we go. Okay. So this is the entry page on jupyter.cscs.ch. So we have a GPU. Alternatively, as I said, with your production project, you could also use the multi-core partition, but we will leave that to the GPU. One node, one arm as the default. And in the advanced options here, this is the place where you should put visual underscore course as the name of the reservation. And this is the place, Jupyter Lab version, where you should select the 2.02 beta testing version. And at this point in time, you click on Launch Jupyter Lab and give it a few seconds. I mean, Slurm, the job scheduler, has to go through all the different job submissions on pitch date before it can give you a node. But this is looking good. As you can see, we are pending in the queue. And there's something interesting here. As you can see, Scratch, there's the name of a log file for each Jupyter Hub, Jupyter allocation which you will do in your Scratch directory, there will be a log file which might help you in case you have problems loading a particular module. This would be the place to go to. Once you have the page running here, you can navigate through your home directory. Here I go to my project page. I go to my visualization training clone of the repository, and I go to my Jupyter Lab folder with the different examples. So to go back to my Matplotlib animation, this would be the place here, double clicking on the file and then running my different cells there. So does this is this clearer now for people? I hope this this clears out the confusion. I'll go back to my presentation here with the hurricane. Okay, so there I was right here. Hurricane Isabel is a hurricane that was created in 2003. And thanks to the NCAR and the NSF Foundation in the USA, we have actually a simulation of the hurricane at a pretty decent resolution. What we have basically are 48 time steps available in a binary file in big engine format with GNU zip for storage. And there are 13 different variables which you can download to your own directory. This is freely available for research, and this was indeed used for a visualization challenge some years back after the hurricane went through. So what I have done for us for this particular demonstration is I have uploaded the QVapor variable in my Scratch directory. So this way, any one of you should be able to load the demonstrations. Now, I want you to look a little bit carefully here at this. As I said, the volume of data for the hurricane is a 500 square by 100 volume. So we have 100 slices in the vertical direction, and then we have 500 by 500 in the latitude, longitude direction. So I have created a function here called load slice for a particular time step, which I call the frame number, and for a particular elevation, which defaults here to 50. So 50 is the mid-range, the mid-altitude, if you want, through the grid. So interesting thing is that I read the data directly from the gzip buffer. And here, as you can see, I slice the data array to extract exactly the K order slice. That's a 500 square slice of data. Now, one more thing that I do in that particular function is that everywhere the data is set to 1E35, this means that there is no data. So I replace that with the not a number variable. This enables both Matplotlib and ParaView to handle the data correctly. Then I reshape the data to be a slice, a two-dimensional slice. And then this flip and rotation is only because I want to make sure the Matplotlib image show gives us the exact same view that ParaView and IPywidget gives us. So the notebook which I have prepared does exactly this. It has that load slice callback, and then the animate function, which basically uses image show in 2D, okay, for a given time step. And this is now something I will demonstrate. As I move my slider around, I will change the animation of my data.
Sorry, John. Since you asked me, it's 5 minutes to 10:15.
Yep.
So for the break. Okay.
Thank you, Rafael. Yes. All right. So, all right. So the load slice callback function to read the data I have developed for you. I have prepared here an exercise. I have prepared here a demonstration called IPywidgets.isabelle.ipy which you can run on PitchDate, and it will load data from my Scratch file system. And it has a particular time slider here to animate the data. I will show you that. And before I do that, I go to the exercise which I have thought of submitting to you. Basically modify the original notebook to add a second slider to slice the volume at different elevation in the Z direction. So this is basically what you should end up doing in your notebook. The time slider we already have, and then have a K slider, which here I realized oh no, this is true. Yeah, if you set K equals 0, this is actually the ground plane, so we can easily recognize the coastline of Florida and then the hurricane data moving through. So let me switch to the Jupyter notebook, which I have live, and it should be this one. There we go. IPywidgets is this one. There we go. So, basically what I've done here is, yeah, this will take indeed a few seconds, maybe a minute, because we have to load 48 time steps. Yeah. And what I recommend is that you change here, for example, this time argument to do a subsampling in time of your animation. This would be much quicker to go through the through the animation. All right, I will try to finish in the next few minutes. So I will introduce the next demonstrations while this particular demo is loading. All right. Okay, my next the next widget I wanted to present is this ITK widget, which you can find under py.org. And this widget I have prepared another demonstration for it called ITK widgets. Basically, I will provide, I have prepared demonstrations of 3 different widgets: the view widgets, the line profile widget, and then we'll see later on a 3D view of the same. And basically, the way I do it, the way we operate the widget is by using view with an image parameter, which is the same image we pass to Matplotlib. And then we can give it additional options such as the color map, etc. So this is what it would look like in our Jupyter notebook. The widget, this is the image show view, and this is the image, this is the ITK view here on the right side of my screen, the ITK view of the same data. And what you see here on my screen is a line profile, and that line profile, which you can change interactively, gives us that particular profile of the data. So I will try to go to my demonstration of it. Switching screen. And then finally, in 3D, using the same view object, we can load the full volume, and I will demonstrate that you can do interactive volume rendering of the same data. So I'll switch, for the last time, I will switch a screen here, go to my Jupyter Lab notebook. So I have executed here the first cell. Here is again the load slice callback to load a single slice of data, and then I have added an additional load volume function to load the full volume. This is the notebook called ITK-widgets.isabelle, which you can also try for your own. So if I load in the next cell here, if I load a single slice of data at time step 48 and at the altitude, at the mid altitude.
Sorry, John, we cannot see the screen.
You cannot see. Oh, I'm sorry. Something went wrong with the Zoom. Zoom. I can't see my sharing button anymore, so there is something. Sorry about that. Okay, we should be back here. Is that good?
Yeah.
Yeah, okay. So I'm sorry. So let me repeat that. There is here the load slice function to load a single slice of data, and then I have added a load volume function to load the full volume. This we will use at a later time. So I'm running here the ITK-widgets.isabelle.ipy notebook. I've already executed cell number 4, which is the basic Matplotlib show using the image show function. And data S is my slice of the volume at the mid elevation. And as you can tell here, this is the later time of the animation. So the hurricane, the eye of the hurricane here is right here at that particular position. Now, here comes the ITK demonstration. Let me go back to cell number 1 or cell number 2. I have imported from ITK the view and the line profile function. So I will view the same here, the same data, which is the data S object. Now, the ITK widget is this particular widget. So it has an annotation panel, which you can turn on and off. It lets you animate your view. If you follow my mouse pointer, as you can tell here at the bottom of my screen, here on the right side of my screen, I actually show the index, the position, and the scale field value of the particular image being shown. So if I go into the eye of the hurricane here, you can see that the value of my vapor content goes up quite a bit, etc. So this gives us a first interactive widget to look at the data. If I bring back my panel, you can see here I have a whole choice of different color maps, etc. to use. And I have a measuring device from here to here, for example, would be size 410, and I have different different options. One last interesting option is the full screen option. Here you should see my animation, my data really at the full screen available. So this for the standard view. I'm going now to the line profile presentation. So I have the same view again, but I have an interactive widget. As you can see, perhaps I should make my screen a little bit bigger. This widget allows me to profile the data at any point in space along my image. So that's a nice interactive tool. And because this is a standard Matplotlib family of widgets, I can always save that image here to my desktop, and I can do different zoom, etc. From, as you can see here, inside my particular function. The last demonstrations to do here is with the load volume. So I'm going to load the volume at time step number 1, and I'm going to display that volume here in 3D. So I now have a full 3D rendering of the volume. Of course, it's a very flat volume because it's atmospheric data. And this is time step 0. If I go now to my time step number 48, there we go. We can see that the hurricane has developed further, and we have a full 3D view of my data. Now, the interesting thing is that now we have a completely interactive way of manipulating the rendering. As you can see here, I can really interactively search through my data set to look at particular features using volume rendering. So this is something we will do further this afternoon to look at 3D volume rendering of data. In summary, this ITK widgets gives us the possibility to do 3D rendering, as I have here in this particular cell, line profiling in 2D with any data set, and we can do more. We can do 3D rendering of polygonal data 3D rendering of point set data. So we really have a lot of options available, and I encourage you to use that. This is developed actively by the kitware company providing VTK and ParaView. So this is really a nice addition to the family of tools which the kitware company gives us. I'll switch, and then I'll switch I want to say screens. Okay, I'm lost again through my screen sharing. This I can. Give me a second, folks, because I have lost. I have lost my widgets.
Maybe it's a good time to do a break.
Yes, it is. It is indeed. But yeah, perhaps let me see, because I've really lost myself. Yeah, we can do the break now since I've lost my views, and then we'll start again. I would start again at 10:45 if people agree with that. Let's do this because I'm a little bit late here in my presentation. Let's do 10:45 to reconvene. This will give people time to try some of those presentations, try some of those examples. People who are more advanced try to do the exercise, and then it will also give you time to raise some questions, and then I will address those questions right at the beginning at 10:45. Okay? So see you in a bit. Okay, folks, this is me again. I'm going to give you some additional information here to help you understand what's going on with the Jupyter Lab allocation. I'm going to share one screen, which is the following one. You should see here my prompt on pitch date. Is that true? Yeah.
No, we don't see that.
Okay, so I missed. Share. Okay.
Yep.
Okay, thanks, Tim. So here I have done an SSH to pitch date, and I have an allocation running currently. So each of you, I mean, if you have an allocation running, if you use the command sq -u and the name of your username, which for anyone else, for anyone, that particular variable .user is your username, you should see a job with a particular number with your user ID. This is mine. And you should see a job. So the particular allocation I have at this time was started at 10 o'clock, 10:04. And it shows that I still have 19 minutes left on the available allocation. So it will disappear once those 19 minutes have expired. It shows that I have one node and 24 CPUs available. And then if I go to my Scratch directory using the environment variable $scratch, and if I look at the last file that was written, here is the log file which I mentioned earlier. So this would be useful for people debugging in case of problems launching the job. As you can see here, the Dask Lab extensions was loaded, my ND reuse was loaded, Jupyter Server was okay, Lab Formatter was okay, Jupyter Lab 202 was okay, and then it throws out a bunch of diagnostics, but basically it shows that nothing is wrong with the current allocated notebook. And as I have as I have modified my notebook, you also see here that it does some periodic saving of the file. So basically that's all there is to it. I repeat, the SQ command shows your allocation, and then going to your Scratch directory, the very last file written in this particular case is my Jupyter Hub log file. And you would notice that, the file name includes the job ID. So if I look at my job ID, this is 26201153, and that's also the name of my log. Okay, so there's no confusion possible there. I'll go back to summarize. I'll go back to my allocated notebook. Which is right here. So what have we done? We've looked at the IPywidgets, which are the standard widgets available to do interactive graphical user interface inside the notebook. And here what I have done, I have modified slightly the original demonstration, but by using the 0 index here to load my slice of data, which means that I'm loading the k equals 0, which is the land-based the bottom of the grid if you want. And this enables me to show the coastline of Florida right here. And then I still have my time slider, which gives me the ability to go through a different time step available on disk. There, so that was the original. Oh yeah, I guess we could look here. Basically, time step 40 is where the hurricane hits the ground. There. Then I have looked at I have presented the ITK widget, which you import in the following fashion here. From ITK widgets, import view and line profile. Here, nothing else has changed. The load slice is still the same with a diff. I guess I didn't put the default here with the value here, K is set to load a particular elevation of the data. Then I have defined a load volume function to load the full 3D grid at a particular time step. Here I have plotted using the standard Matplotlib image show function. I have plotted the data S slice of data. And then I've used the exact same two-dimensional image data to look at it with the ITK widget image viewer using that particular syntax, view image equals data S. And this gives me that particular view widget. I noticed that my widget is currently broken here, but still we have the display available. The mouse pointer here gives me a way to interrogate the value of the image. This could be interesting to find both a problem in the data and then the index in the grid, the IJK position in the grid of data that is failing. The line profiler gives me a nice 2D profile view of the same data. And then finally, I have done a load volume to get one complete time step of the data, which I view using the same code, the same function code, using the ITK widgets. And this gives me a live 3D object where I can modify at will the characteristics of the 3D volume rendering and also the time step. So we said that the hurricane hit the ground at time step 40 more or less. So this would be, of course, my notebook is not live at the moment, so I currently have only the cached version of the 3D data. Okay. Anyway, I will summarize now, and because we need to go on with the rest of the program. I'll share my presentation slide. To finish up by saying that we can do the same Matplotlib animation using batch mode only on pitch date. So if you load the Dane GPU module, the FFmpeg module, the Pi extensions, and the Jupyter Lab module, you can use Jupyter and convert with the option --2 equals Python. You take an existing notebook and you convert it to a straightforward to a standalone Python program, which you can execute with Python. And doing this would save directly your MPEG video or any other animation you have created in your notebook. In summary, we've looked extremely briefly at the big heavyweight applications such as VisIt and ParaView. I've provided a couple of scripts to help you connect your desktop applications to a VisIt server or a ParaView server running on Pitsdanes. I've demonstrated the use of the VNC desktop where you can run any OpenGL application of your choice on a compute node of Pitsdanes. We've looked at different widgets to run inside Jupyter notebooks, namely the ParaView display widget, which is provided by NVIDIA, the standard IPywidgets, which let us build some nice and simple graphical user interface. And we've looked at the ITK widgets for advanced viewing. Now, what I will discuss in the next section is not so much data formats, but really data models. And of course, with a focus on VTK-centered visualization, such that we can load the data both using VisIt, ParaView, VTK, or using the ITK widgets, which I haven't mentioned, lets us visualize not only NumPy arrays or Matplotlib images, but any VTK object. That's really where everything ties up, it gets tied up together. We can alternate, we can really use IPywidgets and ITK widgets for quick prototyping, and then we can use the more heavyweight applications such as ParaView for a full-blown application. Okay, so I'm back here live. I need to get to the next slide, which will take just a few seconds. Okay, so there's my discussion about data format. Really, the focus of this discussion is to look at again, like I said, data storage from the point of view of VTK-based applications. And I like to distinguish between the VTK file formats with an S because there's the so-called legacy format, and then there's also the XML-based format, and then the VTK data model. Now, if I look at my ParaView installation, for example, and I search for all class names with the star reader keyword, I find 163 different data formats supported by ParaView. So the first lesson to learn here is really people should make a good effort at finding a data format that is already supported by the application. So I've listed 163 different formats for ParaView. VisIt has about the same list of formats. And really, there's a wide variety of formats supported, which would be nice to adopt for users. And based on those considerations, I want to go through some lessons learned and then look forward to doing big data visualization in terms of deploying a parallel visualization solution. And then we look also at time series and ghost cells. So a couple of pointers. Last year at the Supercomputing Conference, SC19, the Golden Bell Prize winner, which is the prize awarded to the computation showing the highest throughput, computational throughput was awarded to a group from ETH Zurich. Well, even though that computation used the full PIDS date machine to run its computation, the output generated by the simulation is actually something very small, just a few kilobytes of data. On the other hand, if you look at the scientific visualization finalist from Supercomputing 18, this is a visualization I have done. The output was 1,000 time steps for 10 gigabytes of data for each time step. Now, the point is, when you do a full-blown visualization and animation, most often you have to reload, restart your visualization script many times. So if we're dealing with a few kilobytes, it's no big deal. If you're dealing with terabytes of data, then it becomes really very important to organize your data in an efficient and parallel fashion. So those, probably your case is in between the few kilobytes and the few terabytes, but please pay really good attention to selecting a data format that is already supported by the visualization applications available. But then besides the size consideration, people should also think about visualization not only to do images, but also to do data queries to find out where a simulation, for example, diverges, to find out where there's a bug in the simulation and where the data output has a particular pattern. Or, for example, simply answer a question like, where is the maximum of pressure in my data set? So I've actually created a demonstration ParaView example, which we will run this afternoon to do exactly this, display the maximum of pressure in a time-dependent solution. So the lesson is, think about finding a data format that is widely available, supported. Think about a data format that allows multiple loads and optionally parallel loads. And then think also about a data format that would optimize the queries for particular features in your data. Now, we cannot talk about data format without talking about grids. So I have put here a pointer into the ParaView documentation, which helps us differentiate between different grid types. And if I take, for example, the programmable source module of ParaView, and if I list all its possible output types, those 3 lines of code here from ParaView simple import star A equals programmable source and then list the available types, this gives us a good idea of the different types of data usually found in visualization. So to begin with, there is the standard VTK polydata, which is usually used for geometric objects. Then there is the so-called structured grid, which is used for example in aerodynamics, for grids which are regular, but which are deformed in space to fit a particular geometry. Then we have the rectilinear grids, which are very often used in atmospheric and climate research because they allow us to define a resolution that is different, for example, in the Z elevation. We have the unstructured grid used in finite elements. We have the image data type, which is basically which is usually the standard fully regular Cartesian grid, which would be perfectly fit for images and volumes, for example, from an MRI machine. And then we have the assembly of such objects, such as the multi-block dataset or the hierarchical box dataset. Then we have the more simpler data types called VTK table, which would be, for example, a comma-separated value set of variables. Or we also have the VTK molecule data type, which is a truly genuine data type now in the VTK distribution. Now, really, this description about data type means that it's far more important to understand the type of grid that one wants to visualize rather than its specific name. Said in a different manner, you can encode data in multiple data formats, but the performance and the implementation detail will really matter when it comes to talking about time series or parallel support. So I've prepared a small demonstration here to try to show you the difference between the same data encoded in two different data formats. All right, so my demonstration, let me think again. Yeah. All right, so I'm going to run ParaView on my desktop here. This will be very simple, and this is something you can also do on your own local desktop. For this particular exercise, we will not need a connection to PitsDane, so that should make it very simple. I will switch screen to my desktop. There. I now have, I'm not sure, let me do it again. I need to share screen to this particular desktop. There we go, here. So you should see my ParaView.
No, sorry, we cannot see it.
You cannot see it, okay. I have to check again. Cancel, share screen. Okay. So you should see my ParaView screen. Do you?
We see a terminal, and back in the terminal,
okay. Let me change again. There we go.
Yeah, now.
So you see my ParaView screen now. Very good. I start from a blank screen, and here I have a list of sources. Then I'm going to generate, at the very big bottom here, a wavelet source. A wavelet source. Let me click apply, and then we get a volume of data here on the screen. And I'm going to explain a little bit what we see. First, let's go to a wireframe model here. We see a cube, and we can count how many grid points we have here in each dimension. We have 21. Why is that? It's because I used the default value of vol extend here between -10, +10, -10, +10, -10, +10. That gives us exactly a volume of 21 cube. If we look at so basically, what are those numbers? Those are the IJK indices in your grid. If I look at the information tab in my wavelet, I see indeed a resolution of 21 cube. I see the X coordinates, which are the bounds, the X, Y, and Z coordinates range between -10 and +10. And then we see one data array called RT data of type float with a particular range between 37 and 276. This is the range of the scalar data available. Now, if I go to that particular drop-down menu here, I can select the variable RT data, and I will color my grid with the data indeed. Then we remove the wireframe, and we see a block of data, a volume of data, colored from blue to red in this particular fashion. Let me look. I see there are some questions here, perhaps. Questions? Yeah, I'm not sure I can answer those questions at the moment. So let me continue with my presentation here. Now, I can turn back the display of my object here to an outline mode, and I can look inside the data. I would use, for example, the slice here, which by default would be the X, the slice perpendicular to the X axis. I can also switch to the Y axis in that particular fashion, or to the Z axis. Or I can do something completely free, like this, and I have an arbitrarily oriented slice through my data. Now you notice that every time I change this here, I have to click the apply button. This could be pretty cumbersome. If you have some pretty quick computation to do, you can switch ParaView to an auto apply mode. So in that particular fashion here, as you can see, I have an interactive slicing tool through my object. Here I'm rotating the object in 3D. I can also translate the object, etc. Okay, very good. I'm going to delete the slice and think again about this volume of data. Now, a grid of size 21 cube is very small. Let's make it bigger. I will go from 0 to 511, to 0 to 511 again. Now you notice that I'm counting, this is 0 based. So when the extent of the grids are 0, 5, 11, it actually means 512 grid points in each direction. So there's now my new volume. If I look at the wireframe, it will be, as you see, a lot more dense, and it's only if I zoom in quite a lot that I see the wires and I see each grid point. There. Now, another way to look at this particular volume of data would be to look at a contour slice. Now, we've seen two things here happening. By default, in ParaView, when you add an additional filter here to this pipeline browser, the visibility of the object above it is turned off. So I can turn it on again by clicking on that particular eye icon. switching it to the outline mode, and now you can see that I have an ISO surface inside the 3D volume. As I move, as I select, as I change the value of this ISO contour, I have here a different ISO surface. Okay. Now I'm going to get to the point of storage and data format. Then, so back to my volume. The size of my grid is 512 cube, and ParaView tells me that it takes 520 megabytes of storage. And indeed, I can look at my view memory inspector, and it tells me that ParaView is using, at this point in time, 1.2 gigabyte of data to load my data. Well, fine. That's good and well. Now I want to load this data in parallel. So I'm going to save it to disk. And this is something you can do on your own desktop as well. If you do save data, here I have different options. And there comes the questions of data format. Which data format should I use? Should I use XDMF? XDMF is a combination of an HDF5 storage and an XDMF descriptor, which is an XML-based file format. Or should I use TIFF? Should I use PNG? Should I use the legacy VTK file format? No, I'm going to use the meta image MHD file format. So I'm going to call this volume.mhd. And I'm going to quit. Oh, it takes a few seconds, I guess. I seem to have frozen my application here. Just a second, bear with me, folks. Okay, there we go. I'm back here. I'm going to quit. I need to switch Zoom to share this particular desktop. Share. There we go. I'm going to show you the content of this file, MHD, volume.mhd. There is, I hope everybody can see, yes? So there is an object type image, dimension 3 in space, so it's a volume of data, it's binary data, etc., etc. It has a size of 512 cube of type float, and then the data itself is stored in this particular file. Now, there's no point in looking at this file. This is compressed binary data, okay? That's the header file which we are interested in loading. So I can load this data in the following way. Now, do people still see my ParaView desk here, my ParaView application?
Yes.
Okay, very good, thank you. So there's my volume. And there's no problem with it. I can still color with the data as I did earlier. Now I'm going to run in parallel And this is going to be interesting because this would be the exact same thing that takes place in client server mode when we are connected to PageDate. Let me do it in a very explicit fashion so that you understand what's going on. I run IPyExec with 4 processors. And I run the PV server, which is an executable. It's part of the ParaView family of application. PV server is the remote side server. There, I run it on my desktop, and it's accepting connection. So it's waiting for connection from elsewhere. So I'm going to say, please connect to my local host. Now you should see again my ParaView screen, and I'm connected in parallel. There are multiple indices in this graphical user interface which tell me that I am connected in parallel. The first one is if I go to the help menu, about, I see both a client information and a connection information. And on the right side of this panel here, the connection information, it tells me I have a remote connection with 4 processes, etc. And it tells me that the graphical card I use on my laptop is a GeForce RTX. Very good. The second thing that tells me that I am running in parallel is that the memory inspector here shows 0, 1, 2, 3, 4 different tasks running the ParaView server. Okay, my screen is blank for the moment. I have not loaded the data. I'm going to load the data at this point. I click apply, and there I am with my data. I can color it, and you'd say, oh, everything is good. It's the same data I had earlier. However, if we look on the right side of the panel here, the memory inspector, something tells me this is not quite right. I have one processor, one ParaView processor using 1 GB of data, and all the other ones are using 220 megabytes. So there's no good load balancing. There's something wrong. Something else, there's another clue. When you run in parallel with ParaView, there is a scalar field called the process ID. And if I color with the process ID, let me set up a couple of things here. I'm going to set that as a single integer. Here's the color legend. I'm showing a process ID of value 0, and I see a single column here, which means that what I thought was a parallel run is actually a run using a single processor to load the full data set. So what went wrong? The answer to this question is I used the wrong file format. The file format MHD, which we thought was pretty clever because it did gzip compression, etc. That file format does not support parallel read and write. So what's the answer to that? What is the solution to that? The solution is to save the data in a PVTK image data file. PVTK means parallel VTK. And I'm going to do just that. So volume.pvti Okay. I'm going to quit. I now have a data set called PVTI. Let's look inside it. PVTI actually shows a subfolder called volume, and I'm going to read that particular data with ParaView. Sorry about that. There, you can see here that there is the full 520 megabyte of data we wanted to read. I'm going to run my MPI exec again. I'm going to connect to it. I'm going to load my data, volume. Here I have the same image I expected, surface, meta image. There we go. And that's very good news. I now have 4 different colors, which means that I have a completely load balanced visualization. The volume has been automatically divided into 4 different pieces by ParaView. And as you can tell, as I interact with the data, there's a little break here in the boundary between the colors. It really shows that ParaView is doing 4 different sub-pieces. I'm going to quit, and I'm going to run not with 4 tasks, but with 3 tasks only. And I connect to my server again. I load my data. Data looks perfect. And I look at the load balancing. There, this is what ParaView did. So what I'm demonstrating to you here is that we have a file format which is able to adapt to the number of processors available for the visualization. If I have 4, divides the data exactly in 4 pieces. If I have 3 ParaView servers, it divides the data in exactly 3 pieces. The pieces don't necessarily have the same shape, but they have the same size in terms of megabytes. Let me go to, I think there are some questions coming up here. Okay, good. So there's ParaView running in parallel. Now the same thing will be executed when we connect to PitsDanes in a client-server fashion. Let me go back to my presentation now. I need to share this particular slide again. So again, we can encode the data in multiple data formats, but the performance and the parallel support will depend really on the exact implementation. So my advice to you is to consult with us at CSCS. If you are still in the phase of deciding on a particular data format, you should prototype, test that your data format will actually support the different visualization scenarios that you want to follow. All right. More about grid types. Depending on the mesh type and the grid types that you use, not all filters of ParaView or VisIt, by the way, will be available. So for example, if you use a VTK polydata, you cannot use the extract subset filter. If you use a structured grid, you can. If you use an unstructured grid, you cannot. So this is again something that you will have to take into consideration if you want to use a particular filter or algorithms available in ParaView. Now, this is a survey I did a couple of months ago when I did the webinar on data format, taking 4 different examples here. An open form data set. Can ParaView read this in parallel? A regular Cartesian grid in the MHD data format. This is the thing I just demonstrated. Can we read that in parallel? Well, we already know the answer is no. The same regular Cartesian grid, if it is saved in the VTI format, and we have demonstrated that the answer to this question is yes, ParaView can read it in parallel. If I have an unstructured grid stored in the VTK XML VTU format, what does ParaView do to it? To replicate the demonstrations I have given to you in live here, you could type the following Python code using PVPython. So I've talked about a family of ParaView application executables. There's ParaView, the name ParaView itself, which is the desktop client. We've talked about a PV server a few minutes ago. PV server is the server-side executable. PVPython is yet another executable available, and it's basically a Python interpreter with ParaView already embedded in it. So using PVPython, you can import the ParaView simple module, create the wavelet. I have done the same thing using the graphical user interface. Set the dimension of the grid, update the pipeline, and then save it in the MHD format. You do this, then you do the same exercise with VTI, and then you can test your parallel support. So this is basically the summary of the demonstration I have given earlier. Here we are showing reading the volume of data with 4 different servers of ParaView. All right, back to my original questions. Will the same thing apply to an open form data set? And the answer is no, unfortunately. MHD, we've seen that the answer is no. VTI, the answer is yes. We can read it in parallel. And then with VTU, we cannot actually load an unstructured mesh in parallel using the VTK XML file format. Let's switch a little bit gears and talk about time series. I have put here in your documentation a couple of links to the ParaView user guide. And I encourage you to click on those links and then visit and read the content of those web pages. I have created a ParaView Python script, which we can execute locally on your desktop if you have done an installation of ParaView, or on PitchDaint, you can run that that ParaView script as well. Now that ParaView script has one important function at the very end. It's the save data function. And the option to that call is to write all time step as a file series. So I'm going to generate a number of image data, which means a regular Cartesian grid stored in the VTI file format. And I'm going to give it a particular suffix here. And as I execute this script, it will write to disk a time series of data, which we can then read back using ParaView. So the last executable from the family of from the ParaView family is PVBatch. PVBatch is something you would use, you can use on your desktop, and this is the tool you would use on PitchDaint to automatically generate a visualization and perhaps an animation, a movie animation of your data using the PitchDaint compute node. All right, so I'll let you do this as an exercise. As you run the executable here, I'm going to do this myself on my laptop here. Just a second. Okay, so I have generated this, and I'm going to show this later in my live demonstration. To read a time series with ParaView, we use that specific syntax, which is dot, so double dot VTI. And this is documented in the page here that I have provided you. Using Python code, once the data is read, using Python code, we will inspect the particular parameter called time step values, which is a member of that reader object. And we will see this series of time step. So this is very important. Those are the time step values allocated to each of the solution we write to disk. So let me, this is perfect time to switch desks again. I'm sorry, there's a lot of switching here, but this is the nature of our presentation. Okay, so you run PVBatch, just like that, with the pv generate image data.py script. And it has generated a series of file called ts index00.vti all the way to number 31. I read this data in the particular fashion, ts underscore dot VTI. I say apply, and I have the standard box, which I use for all exercise. I have one scalar field called scalar A. Okay, that's it right here. But now if we look at my information tab, I have here a list of index going from 0 to 31 with a value of 0 to 3.1, and those are the time step values. Okay, I have a grid size of 24 cube. This is something pretty small. I've done this for the purpose of the demonstration so that you don't fill up your disk with heavy data. And what else has changed in my user interface? I now have a current data time here under the data arrays panel. And I have a play button, which I can play. There we go. So I have basically an oscillating set of scalar data. There. Going to the Python shell. And if you do not have a Python shell yet, this is what you should do. View Python shell. So you instance a Python shell panel, and at this point in time, you have access to all objects in the ParaView interface. So this particular object, which in my interface here is called TS, that's not a very nice name. I'm going to call it data time series, like that. It's kind of a long name. Now, ParaView has a set of get active functions, which are pretty nice. There's the get active view and also the get active source. So if I say reader equals get active source, I can now look at my time step values. Okay, so this is exactly what you have on page 18 of my presentation. I have gotten a Python handle, an object, which is a handle to the active source loaded in my ParaView pipeline. And then I have a time step values array, which gives me basically the set of available time step. Now, how do we change the time step inside the ParaView application? And that's very important. Of course, I can say play, just like that, stop. I can select the time step anywhere through this list. For example, time step value number 2, etc. Or I can drive the execution of my visualization pipeline from the view object. So if I do a get active view, this view object has a parameter called view time. And as you can see on the left side of my screen here, the view time is set to 2, and it matches what we have in our graphical user interface over here. If I set it to 0.9, and I code again my Python shell, I have a value of 0.9. So basically, the Python shell is in sync with the graphical user interface. Now, the data as time step 2 here looks almost completely red. High values? Well, not necessarily. It means that it's using the standard minimum and maximum that were calculated for time step 0. Okay? So if I go to time step 2 and I click on rescale to data range, here I have again a wide spread of colors for that particular set of data. And I even have a button called Rescale to Data Range over all time steps. And this is pretty nice because here it tells you exactly what it's going to do. It's going to find the global minimum and maximum of the data over the whole time step. And ParaView is pretty smart. It tells you, are you sure you want to continue? What does that mean? It means that the whole time series of data would be loaded one at a time into ParaView just to calculate the minimum and the maximum. So this could be pretty wasteful. So if you know what your minimum and maximum are, you should indeed set that directly into your Python script. Okay, I got a couple of questions that I'm going to answer here. Julia is asking, can you change the format of a mesh once loaded into ParaView? Well, that's a very good question. And the answer is very long. I could spend a half hour. Just kidding. The answer is it depends. And I'm going to demonstrate that right now. So, demonstration. What is the type of this data here? This data is of type VTK image data. It's a regular Cartesian grid. Okay. In the user interface, it's also called uniform rectilinear grid. That's fine. Now, this is a data volume, right? If I want to only show the outside surface of my volume, I have a tool called extract surface right here. Now, the display looks exactly the same, but this is indeed just a surface. Let me prove that to you. If I make it semi-transparent, you can see that it's just a surface. Okay, let me make it fully opaque again. Let me switch back to the volume. If I make the volume semi-transparent, well, I guess it looks the same. Okay, forget about that. Back to my extract surface. Back to my extract surface. What is the type of this object? The type has been changed to VTK polydata. This is a polygonal mesh. So I have indeed changed the data, the grid type of my data from a volume data of type uniform rectilinear. I have gotten a polygonal mesh. This is one example. If you want to, you could also resample with you could resample your data. No, here's another possibility. If your pen data set, the type has changed to unstructured grid. So look at it. I have a volume of data with 12,167 cells. Those are voxel. I have changed its type to an unstructured grid with the same number of cells, but those are hexahedral. In fact, if I look at the spreadsheet, with the append dataset object, if I look at my cell data, this tells me that the cell type is voxels over here. And well, interestingly, it tells me that the cell type is always voxels, but it's a documentation issue. Here in the append data set, I have an unstructured grid, and I guarantee to you that the cell type is hexahedral. There. All right, so I'm basically done here with the demonstration, and we've already introduced quite a bit of features of ParaView. We've seen this spreadsheet view, which you instantiate in the following manner. If I want to look at the histogram of my data, I would do it like this. There is a histogram of my data. Perhaps I went too fast. Let me redo it. I create a view called the histogram. The histogram is empty. And then I select the object and I make it viewable, the object that I want to show. In parallel to this, I can use a spreadsheet view. Okay, we've seen it earlier. I select here the object that I want to look at. Okay, I have the structured coordinates here as one column of data, and then I have one column of data called scalar A. And this is indeed the floating point scalar field which is loaded in this volume. And we know from this particular panel, the information panel, that the minimum value is 1.16, the maximum value is 2.84. This is for the current data, this is for the current time step loaded. Now, in this spreadsheet view, I have a very interesting feature. I can sort data by their scalar field value. So if I click in this particular fashion, I have the data sorted from top to bottom. And if I click it like this, I have it sorted from minimum to maximum. And indeed, the minimum is 1.16. It matches the data I have here. Now, visualization is not only about making pictures, it's about doing data inquiries. If I wanted to look at the 10 smallest value of the scalar field in this grid, how would I do it? I would do it in this particular fashion. Watch my mouse pointer. I have here sorted the data in increasing order. I'm going to select 10, 0 to 9 values. And those values, well, we don't see them right at this time because the object is not visible, but now I see them. In the data time series selected, if I make the same object viewable in the same 3D view, those purple points are exactly the nodes on my grid which hold the 10 smallest value of my scalar field. Okay. Now, here I have the coordinates. So I know exactly the ijk coordinates of those points. So if there is a for example, a bug in my simulation, I can find exactly the IJK coordinates in my grid, where to look for a possible problem. Now I can extract those particular data by using the filter called extract selection right here. As you can tell, the point ID, which is the vertex ID, which I had in the, there we go. Those point ID match exactly what has been copied over here as the selection of points. If I apply this, I now have in my display exactly the four. When you do it like that, let me make them a little bit bigger because we don't see them. Here are the points. Okay, I'm sorry, 10 numbers in my grid over here are exactly the data matching my particular criteria. And I'm going to do a final demonstration here of the ParaView interface. Remember my question about finding the maximum of pressure. So, okay, in our case, the scalar field is not called, it's not called pressure, but it's called scalar A, but that really doesn't matter. So there's my volume. I'm going to go to the Find Data menu, select the point in my mesh where the scalar is maximum. And I'm going to say run the query. And then I'm going to say plot selection over time. Look at my query here. The query is find the scalar value equals to the maximum and run this over time. When I say apply, there's my interface. ParaView has automatically loaded all the data, all the time step values, I'm sorry. It has searched for the maximum of the scalar field for each time step. It has drawn a graph in an XY fashion with the curve connecting all those maximum points at the different time steps. And the green line that we see here shows exactly the time step where I am at the moment. So this is time step 2, as you recall. Now watch, if I go to a different time step, 1.2, the green line here has switched back to 1.2, and it tells me exactly where in the graph I am currently located. And as I animate my display, we're going to see this move along. There we go. So let me reset to time step 0 and animate. So this gives us, if you want, a linear in time, a linear indication of the maximum of data in that particular volume. There. Is there any question on this particular demonstration here? Basically, I have loaded a time series of data. I have shown to you how I can extract some data following a particular criteria. For example, find the 10 smallest value of the scalar field at a particular time step. I have demonstrated to you how I can find the maximum of that scalar field for all time steps and do a graph of that particular variation. And basically, that's what ParaView is about. It's just, it's not only about doing a nice 3D graphics, but it's really about query and analysis of your data. All right, I will switch screen for the last time, and then we will all take our lunchtime break. There, I am back over here. So this is, I repeat, this is an exercise you can do also on your own laptop because it generates the data locally. In summary, you generate the data with PVBatch. You load the data in this particular fashion. You can inspect the time step values looking at the reader object. The last slide I have is about ghost cell support. So there's one pointer here concerning that particular topic. I don't have time right at this moment to demonstrate this, but this is again very important in terms of the choice of data format. You should ask yourself the question, does the data format that I use allow the encoding of ghost cell values? Or can the data format that I use enable ParaView to extract ghost cells for a particular feature? Because depending on the filter that you will use in ParaView, different levels of ghost cells will be required, and your data format needs to support that. A quick survey here, because this is interesting for the webinar that we will conduct next week at CSCS. This is about the ADIOS file format. So Samuel and myself are going to talk about ADIOS next week, and I would like to know ahead of time if people are using the ADIOS file format already, if they plan to, if they've heard of it, if they have some specific questions about it. So when we come back to the screen here at 1:30 after the lunch break, I will run an interactive survey where each of you can vote on that particular topic. Now, finally, if your data I/O is too heavy, regardless of the file format that you're using, the solution is to use in situ visualization. And this is also something that we will discuss next week with Samuel. So I have an example currently running at CSCS on 4082 compute nodes. Now, if each compute node were to save its data to disk, it would slow down the simulation considerably. So the solutions we have adopted is to do the data extraction and filtering in situ using the ParaView interface, using the ParaView API, if you wish. And then we save to disk not the full volumes, but only the geometry that we use for the rendering and the movie animation. So if your data, if your simulation is very heavy in terms of I/O, then my encouragement is really to move to an in situ solution. As a closed parenthesis, well, there are 163 data formats supported by CSCS. As I said, supported by ParaView, but still sometimes we come up with big simulation codes which are used by a large community of people. And in that case, it is worthwhile creating a new reader. So this is an exercise I have done for 2 communities of simulation, the people using NEC 5000 from the Argonne National Lab, and then the people using the Gadget 2 HDF5 interface. So if you are one of those people running computation on pitch date with NEC 5000 or Gadget 2, please consult with me. There's a native parallel reader to support this data. That's basically my summary. Choose well when you select a particular data format. Make sure you can encode multiple time steps, collections of files. Make sure you can read your data in parallel. I have demonstrated to you how you can test and prototype the parallel support for your data format of choice. Make also sure that you can read a subset of the data. For example, when we looked at the hurricane data this morning, we only loaded a single slice of data through the volume. Well, this was done because using NumPy, we can do array slicing. So any format which you can use with NumPy would be, for example, a good candidate to do subsampling. So keep that in mind. If you have questions, please use the chat. I will try to look at the questions over the break. And when I start again at 1:30, we will go through, first we will go through the questions that people have raised during the break. And with that, I thank you. I wish you a good lunch, and I see you at 1:30.